So we're talking about rotational kinetic energy and work. Rotating objects has rotational kinetic energy, just as translating objects has translational energy. Okay. So back in the day, we knew that K, kinetic energy, was equal to what? What was the equation for that? 1 half mv squared. So if it's 1 half mv squared, what acts like our m? We're going to keep the 1 half. What acts like our m, but in rotation form, it's not just mass, but yeah, it's inertia. Or mass is a type of inertia. Well, here's our rotational inertia or moment of inertia. V. V was velocity. Do we have something similar to that in rotation? Omega, good. Okay, so we have omega, which is similar to it. So 1 half I omega squared. That's our rotational kinetic energy formula, okay? And it's similar or the same to it. The units for this happens to be, well, what's I's units? Is it blanking out? The screen is blanking out. So we said that the I has a units of kilograms meters squared. So kilograms meters squared, and omega has a unit of radians per second squared. Okay. Sorry, radians per second. You're right. Radians per second. I heard you, but then I'm going to take that and square it. Okay. Now, radians is just relative to the radial length or the radius. So if I see this, I would say it's really just kilograms meters squared per second squared. Okay. But then I could also just say that it's kilograms meters per second squared with another meters. Mass times acceleration. It really just is Newton meters still. Okay. Which means the units for energy is, yeah, joules. Newton meters are joules. Okay. Remember work, power, energy, that unit. Work is joules, energy is joules. But it's really just Newton meters, which is a kilogram meters squared per second squared. Okay. So when a tangential force is applied to a rigid body at some distance r away from the axis of rotation, the object will exhibit angular acceleration. Okay. So if we said that our work equation, what was our work equation back in the day? FD cosine theta. Force times distance cosine theta. Well, that is the work is the force that is in the same direction as the distance. Okay. And if our tangential force applied is what's rotating it in that rotational direction, okay, then we could say that work is just force times the change in distance around the rim of the wheel, right? But also that going around the rim of the wheel, that distance is r times theta. So why don't we just plug that in? Fr change in theta. And if torque is Fr, do you see an Fr over here? Okay, so if that's torque, we can say that W rotation is just tau change in theta, or torque times the change in the rotation. Okay. All right. So if these are simply just the same equation, just with different symbols, it really has the same components making it up. We can say that a couple of things remain true. Conservation of energy. Okay. That remains true. And the other thing that will remain true is the work energy theorem. Okay. Conservation of energy. Energy is never created nor destroyed. But we lock into the can be transformed part, right? So our rotational energy could come from a linear motion. Okay. Like if somebody were to slap somebody's head and then their head rotates. Okay. Or where we saw this was we had a bullet fired into a block of wood and it swings up on a pendulum. Well, that's on a rotation. Work energy theorem, what was that? Work energy theorem. It's exactly like it sounds, guys. Work is the change in kinetic energy. Okay, so work changes energy. Doing work adds or subtracts kinetic energy. Kinetic energy for linear, we have 1/2 mv squared. What's the cognate? What's the similar form of it for angular? 1/2 what?
I omega.
Right. I'm asking what's in the boxes up top. So this will be I omega squared. And then down here, work is... So we can write work is torque times the change in the rotation. How much it rotates. Okay. Here's the work energy theorem. Work is the change in kinetic energy. So we have that equals 1/2 mv squared minus the initial 1/2 mv squared. So for us, work is equal to the change in kinetic energy that's rotating, not just translating it, not just sliding it, but now rotating it. And the work that is applied to rotating it is 1/2 I omega squared. And that's the final minus 1/2 I omega initial squared. That's kinetic energy. That's kinetic energy. Initial minus, sorry, final minus initial.
Just remember the sorority. When if you forget work, it's delta theta tau. The fact that this exists is funny.
All right.